2 minutes here. All slides, type default, links and download. Presentation display 2. Okay. Slideshow.
Yeah.
There we go. Yeah. Cool.
Reminder, you have 40 minutes.
Yes. Including questions. Okay, so it's about.
And so for some interesting or good questions, you can refer them to this card.
Okay.
Like
Yeah.
start, so.
Okay.
When you have 15, 10, 5, and 0 minutes left.
Okay. Cool. Okay. No, no, I can introduce myself. Yeah. Yeah. So, hello everyone. My name is Marcelo Tosatti. I work for the Red Hat virtualization department, and I'm going to be talking about migration. So the first thing is that it's this slide. The name of the talk is a little pretentious because it's not actually a look at virtual machine migration algorithms, but just a part of migration, that is the choice of page to clean. So, how does the pre-copy migration mechanism work? So we want to migrate a live VM between 2 hosts, and we copy pages sequentially until a configurable threshold is achieved, and when the threshold is achieved, we pause the guest on the source host, transfer the remaining pages, and resume the guest on the destination host. So with this scheme, there have been some problems reported by users that certain workloads fail to converge because the speed at which the guest CPU writes to memory is higher than the speed which the migration stream is able to clean pages. So there are 2 solutions in place for this. One of them is vCPU throttling, where the guest is paused for short periods of time to reduce the speed which the CPU is able to write to memory. And then there's post-copy, where the guest vCPU is moved to the destination host, and then the pages which have not been copied are copied by a thread. So when if there's a fault on the destination, the fault will transfer the page from the source and resume execution. Both of these solutions have drawbacks. So vCPU throttling causes latency spikes, and post-copy also suffers from remote faults causing latency spikes. So I wanted to know if we can improve migration in some way. So what I did was to create a model of the migration procedure. So, and then we were able to draw some conclusions from that model, and then we did some simulations to simplify testing. And so in a model, we tried to build a simplified version of the real thing, such as building a rail model, and then derive conclusions applicable to the real-world scenario. So what metrics are we interested in? Basically 2 metrics. What is the maximum number of clean pages achievable, and how long, which translates to thresholding, migration thresholding QEMU, and how long it takes for that threshold to be achieved. So about modeling, how do we model CPU and network? The CPU writes to memory in sequence with a given speed, and the migration stream cleans memory with a lower speed than the CPU writes. So there's a ratio between the CPU and network. And in the model we call writer, it's the sequence of integers, a sequence of integers that represent the numbers that the guest writes to in memory. And then cleaner is a sequence of integers representing the page numbers that the migration stream sends to destination. So yeah, I wrote this for the migration guys that when they see writer, they should think guest CPU writes, and when they see cleaner, they should think migration stream. So visual representation of the model. On the top, this top squares represent memory, and you start counting from 1, 2, and so on. And then here you have writer, the sequence of pages that the CPU is writing to, and cleaner, the pages which the migration stream is sending to the destination. Then we divide time in slices. So, for example, here we have time 0, this slice for time 0. And then writer is able to send 1, 2, 3, 4, 5, 6. So writer in this case is 6 times faster, CPU 6 times faster than the cleaner, than the network. And then in this model, just for illustration purposes, the dirty pages are white and clean pages are purple. So in the first time slot, we clean page 1, and on the second time slot, we clean page 2. And since writer has not written to page 2, in that period, it remains clean, and so on. And this is an example to illustrate a slower, cleaner, slower network bandwidth. So cleaner is 12, I guess. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, or 13. I don't know, lost count somewhere here. So, but it's much, the network is slower, so you can clean less pages. And what happens is that on the on real systems, we don't know what the access pattern is in the future. So this we don't know what will happen from. You just know what has happened in the past. Let's say that you're in the first time slot. You don't know the future. So in the model, we have the ability to fix the future, and we know what will happen, so that we can analyze and find the best possible choice of pages. Yeah, so in model systems, we know the future because we fixed that. So given that we know the future, what is the best page to clean? So this is an example where we have a writer sequence that is writing sequentially. So we have 1, 2, 3, 4, 5. And the, let me see here again, 3, right? So the writer CPU is 3 times faster than memory. And we could, in this window, in this time window here, we can select pages 4, 5, 6, or any page actually. But for demonstrations, if we select 4, the page 4 will remain clean for during the time period between this window and this window. So it will remain clean for 1 unit of time. But if, on the other hand, we choose to clean page 7, the page 7 will remain clean for a longer period of time, for 2 units. So just to illustrate what difference the choice of page makes. So given that, we have that from a position in the writer sequence, you can always find a page which is farthest, has farthest access in the future. So for example, in the first example there, we have page number 10 at position 10, is farthest, and this arrow below represents the length of time that the page 10, in this case, if you clean 10, remains clean. And then on the second example, we have a different pattern for the writing, and then the difference is that we also have a 10 here. So 10, if you would represent how long page 10 remains clean, it would be this arrow. So it's of course smaller than the length of time that page 9 remains clean. So 9 has the farthest access from position 1. And if we again replace 9, have 9s here in the right pattern, then 9 is the furthest access in the furthest page from position 1. So if you think that this arrow represents the length of time that a page is clean, then by cleaning several pages in sequence, you increase the number of pages that are clean at the same time. So you want to, and that represents the threshold in QEMU. So the length in this direction of the intersection of these ranges is the maximum number of clean pages, right? So if the point at which this is highest from there, from that point below, is the number of pages that the maximum number of clean pages. So then you can ask what is the optimal cleaner? What is the optimal way to choose pages to clean? What is the best possible choice? So the best possible choice is the one which selects the page which has the farthest access in the future, because that will result in the highest amount of clean pages available and for the shortest amount of time. So for example, here we have that if you switch the page 1, position 1 from cleaning the position 5 to cleaning the position 3, we see that this length has decreased, right? So yeah, so that is the farthest. Always choosing the farthest position is the optimal cleaner. Yeah, and I just said that the optimal cleaner is the one which chooses the farthest page at every position. And then, so what is the maximum number of clean pages? The maximum duration that a page remains clean is given by M, which is M is the length of the writer sequence. So and then R is the ratio between CPU and network. So if you clean page 1, let's say, and you have R equals 3, you're going to walk the first time unit, you're going to walk there, and then the second there, and then on the third there, and on the fourth there. So it's the given page will remain clean by at most the length of writer divided by the ratio, because the writer cycles back to that page in that amount of time. So in that time that a page can, the maximum amount of time that a page can remain clean, the cleaner can clean up to M-1 divided by R pages. So that is the lowest threshold that you can set. So if you start with M 30 pages and you can clean up to M-1 over R, that is the maximum, that is the minimum number of dirty pages that you can have. So the consequence is that the threshold, it depends on the number of pages in the workload, and some other things I will see later. So in the real world, what is the maximum number of clean pages? It depends on on how far you reaccess a page. So if you have a few pages that have reaccess time very distant, and then you assume that you have a large number of those pages, then that determines the maximum number of clean pages available that can be achieved. So the migration stream will be able to clean in that time the duration of that a page remains clean divided by R, which is the ratio of CPU and network. So a practical example of ratio is modern Intel Xeons have 50 to 8 gigabits per second memory bandwidth, and with like 10 gigabit Ethernet, rounding down to effective 5 gigabit, would give you a CPU net ratio between 10 and 17. So then, to test these conclusions, I wrote a simulator that to compare the sequential cleaner, which is QEMU's way of cleaning memory. It goes 1, 2, 3, and to the final page, and then restarts again. So I wanted to compare the optimal cleaner, which I just described, with the sequential cleaner in QEMU. So I took a writer sequence with 30,000 pages, and then did some variations. So CPU net ratio 3, 5, and 15, and 15 is pretty close to what we have today. And number of pages is number of pages that you repeat, and I'll describe this later on. And then scrambling is a parameter to simulate random access. And so we start with a sequential writer. So, but then we want to simulate some pages having higher frequencies. So what we do is I wrote a Python script to, from that sequence, I have a few parameters. That one of them is distance. So I take page 1, for example, and then I copy it a number of times, and with a given distance. So in this case, distance was 2, so I copy 1, and then 1 again, distance 2, and then 1 again, distance 2, and then 1 again, distance 2. And then I would vary the number of copies that I made and the distance. Yeah. So this is another example where we have, when I chose to copy 2 pages, and then the effective distance ends up being not being 2 as I specified, but 4, because you have to count the distance of the one that is also being copied, but it doesn't really matter because it's approximately is fine for testing. It doesn't have to be precise. And then the last thing was scrambling, which is we take the writer sequence, and then we randomly select the position. Then we randomly select the distance from that, and then we swap the two. So that simulates random access. Yeah. So, for example, if you comparing the sequential writer with the sequential writer and the sequential cleaner and the optimal cleaner, we see that the maximum number of clean pages is very similar, but the time to reach that number of maximum number of clean pages is 2 times higher with the sequential cleaner, which is QEMU's cleaner. And why is that? It's because the optimal, for the sequential writer, the optimal pattern to clean pages is to be behind, just behind. So if you write a page on the next time unit, you have to clean that page. And so the writer, the sequential cleaner, it will take some time to get in sync with that. So like if you rotate if you start on a position, then you have to wait this writer to cycle until it's right ahead of the cleaner, and then you get that the minimal amount of clean pages. But sometimes it might take time to get to that position, so that's why it takes more time. And then these are the results from the simulation. That's just the output. So here we have in blue we have the optimal cleaner, then red the sequential cleaner, and then on this axis we have the maximum number of clean pages and the number of pages, as I said earlier, as described earlier. So as we increase the number of pages that are repeated in the writer sequence, the maximum number of clean pages increases, which is expected. So maybe you don't see this, but both are in the same line here. The optimal and sequential are on the same line. And but yeah, this is useful so that we see that if you have a workload with some pages that are higher frequency and other pages lower frequency, then you have it allows you to have a smaller threshold. Yeah. Then, if you increase the number, maybe I didn't say that, but the optimal and sequential are on the same line there, so they have the same results for the maximum number of clean pages that are achieved. But the sequential cleaner for the time it takes to reach the maximum number of clean pages is much worse, right? So it's about 2.5 times worse for a few pages that are repeated, and then it starts getting worse and worse, and then suddenly it gets really worse, like twice as bad. And then with scrambling, that simulates random access, we have that the sequential cleaner it starts. So this is just a few pages being scrambled. So every one scrambled pages means one page that was swapped, as I described above. And so as you increase the number of pages that are scrambled, that are not sequential, the maximum number of clean pages that are achievable also grows down. So that's pretty bad. And the optimal stays constant. So it's resistant to random workloads. And then for the time to reach the maximum number of clean pages on the scrambling case, we have that again optimal is constant, and sequential is it starts, so that's like 10,000, and then you go to 6 times worse. And then as you increase the number of scrambled pages, it gets worse. And here I think, I haven't looked in detail, but I'm pretty sure that, I guess, I don't know, that you scramble, when you choose pages randomly, you just scramble them back to their original position. Like you choose randomly and then you switch them back, so you get back to performance that was before. But anyway, it is useful to realize that, this thing, this delta there. So the conclusions from this study is that the order of page selection on QEMU can be improved, that the sequential cleaner has non-deterministic results, so that depending on where, if you have a sequential writer, depending on when you start the QEMU migration, you'll finish on different times. And that we can test selection algorithms outside of QEMU, and that makes it much simpler to simulate and test all kinds of scenarios. And also we get upper bounds on the on the how fast can migration be, and what can you change in your workload to improve this metrics if you care about such things, and yeah, so this was adapted from Beladi's mean algorithm. This idea that you choose the page that's furthest in the future. Is a guy named Beladi that did this for LRU for page caching, and that's it. So this is those are the results that I got, and yeah.
Did you, during your simulation, did you take into consideration different NTU or different network latency?
No, yeah, so not latency, but just throughput. No, we not. I'm not considering latency. No, just throughput. So just number of pages that I tried 3, 5, and 15, and then the ratio, right? So net is 3 times slower, 5 times slower, and 15 times slower, and the results are similar. This that I plotted here are the results for 3, ratio equals 3, but the results are similar. Yeah, I saw those.
I mean, maybe there is way, there is space for upgrades from the point of you can have dedicated line just for migration, like for example Younger does, and you can tune it on this way.
Sorry, can
Line for migration, network line, can be separated from the others, and maybe you can do just tune there, just for demigration, sorry, nothing else.
Right. So this is for these numbers. They have been. These are constants. They represent a constant bandwidth. So if these numbers are if you have a network that they already represent a network that's exclusive for the migration. So yeah, it's just complicated. If I wanted to try like varying ratios, I don't know. Maybe I could do that, but it would get more complicated. I haven't done. Yeah.
Follow-up question: you assume the writer and the cleaner have a constant rate?
Yes.
Is that true in real life? So that, for example, is the cleaner unrelated to the writer performance? Is the cleaner performance of number of pages that it's cleaning is constant?
For sending pages, I think almost constant. But for writer,
Also finding the right page to do it in the optimal way.
yeah. So the bandwidth in real life, if you have a separate channel, it should be constant, right? I think that if you ignore the network card specific details and load on the network, it should be constant. But the writer is not in a real life. You have you write page and then you wait for something and then you, yeah, we're not simulating that. But the worst case is writer writing all the time. So the case that we had problems was with people that had workloads that the memory was constantly being written. So that's what.
And the cleaner is not affected by it? Because after all, it's running the same system, the same CPU. I know probably not different thread of QEMU, but.
So the question is if, well, I think you'll get more bandwidth available if the writer stops writing. Yeah. So yeah, I could try to simulate this, but I haven't. Maybe I should try as well this variation as well to know. Yeah.
You mentioned at the beginning that you could slow down the CPU, right, for the process.
Yes.
And could you give a comparison on this model versus slowing down the CPU so you get a lower delta between the writer and the cleaner?
So with throttling, what happens is that I haven't.
Maybe throttle increases the
It
slowdown as you
at every what would happen is that the R here would this thing. So what happens is that if you let the CPU write, you get like 50 or let's say 6 gigabytes per second. But then with what the threshold thing is doing is at every I don't know, at every 100 milliseconds it will stop, it will send a signal to the vCPU so that it stops for a very small period of time in the hope that it doesn't affect the workload negatively. And then it will reduce the amount of memory, like from 6 gigabytes per second, it will reduce to maybe 4 or maybe 3, depending on for how long you stop. So that's what would happen.
Yeah, but how does that compare as a you know?
I think it would just reduce the ratio, but the problems with the cleaner would be the same, because you would still not choose a page that is gives you the maximum length of time that page is clean for. So the same thing is valid. Just the ratio would be affected, I think, in the model.
No, I was just going to say, I'm curious to see how it compares to, like, just the kernel pages out. How does the kernel pages do make in cache? Right, these are anonymous pages, right?
So these are the cleaner in QEMU. The cleaner is operating on physical address pages, pages. So it goes from physical page 1, physical page 2, physical page 3. That's the sequence it cleans pages. And I think when you if you boot your machine, if you boot your machine and you run a sequential, I mean, if you boot your machine, if you boot your host machine, then you boot your guest machine, you get your pages in sequence. Like they would be the pages that you have are the virtual pages are in sequence with the physical page. But in practice, you get probably you get allocations that are spread in memory. So even if you do if you use a workload that's writes sequentially, that will end up not being sequential in the physical address range. So yeah, but was that your question, or you say that?
It seems like a very similar technique that you would have to use in the kernel to figure out under memory pressure how to make pages, right?
Right.
So have you looked at how the kernel selects pages?
So I've been talking to Karen about improving this. So this is just we're finding what happens, and then we want to improve. And then one idea that we have is to migrate to collect frequencies of pages, and then separate pages in lowest frequencies up to high frequencies, some number of classes, and then migrate first the pages which are lowest frequency, and then go up to migrating the other ones, because the ones with low frequency should give you the largest amount of page time that is clean. So yeah. No.
Some of them are more prone to being rewritten during the migration than others.
Right, but in KVM we map with EPT. We map pages with writable, always writable, executable. So from KVM we don't have that information, but we could walk page tables perhaps, or have some sort of on live migration, you enable pages, you capture the kind of fault. Perhaps that's some useful information as well that can be used to decide, to infer whether the page is going to be accessed in the future. Yeah, you're right.
Maybe as the guest agent to tell you, basically hope to some ranges.
Yeah, could have interaction with guest agent. And another thing I was thinking that we could have a mode that asks if we go changing having interaction with the guest agent, we could switch to a mode where kernel allocator is reduces to a small subset of pages, so it doesn't try to write to hand over allocations for memory spread in memory, but just a small subset, so that the activity stays there, and that would help reduce the time as well. Yes, just small, just for the duration of the migration. Then it would improve speed as well, migration speed. Okay.
So, have you tried the simulation with some type of algorithms that can be used?
So, no, not yet. So, the algorithm is like this. I'll show you. It's to find this optimal cleaner, you have to find a page which is farthest, right? So you, from a given position in the cleaner sequence, you have to look at all pages. So you start there, and then you start recording, and then you say, is that page accessed again? And then you loop again, and then you go next page. So it takes a long time to find the cleaner given a writer. So it's not very practical, and you don't know the future. But we're thinking, one of the things that we're thinking is to have this frequency, collect frequency of pages, and then divide the memory in pages that are accessed most frequently, less frequently, some number of classes.
You didn't run the simulation?
No, this is just the optimal and the sequential cleaner that has been run. Okay, so thanks, and yeah. Yes. Yeah. Just.
You would need a page,
Yes.
and then the guest needs to forward what to write again.
To that page, yes.